Okay, I would like to show you a couple of videos before entering into the class. Okay, now in the last class, what we discussed, just a recap, just 1 or 2 minutes, 1 or 2 minutes. Then we go for the today discussion. Okay, now yeah. Yeah, we discussed shaft. You should know the what is the shaft and where we are using shaft, right? And shaft mostly we are preparing, we are designing the shaft dimensions, the range from the shaft diameter, mostly 5 to 200 mm. And where we are applying the shaft for applications, wherever we are using gears, pulleys, brackets, for example, shaft is important role. But even though we are going to see some of the other applications where we are using practically shaft. And the axle, we discussed axle in especially in automobile vehicle, four-wheelers, right? Front axle and rear axle. I mean, mostly the axles are, I mean, non-rotating shaft, non-rotating, right? And here only supporting the wheel supporting as well as the allow the wheel to rotate. That's what we discussed in the last class. So but the shaft is rotating part, axle is mostly non-rotating part. But the spindle is, I mean, spindle is small length of the shaft but slightly tapered design, slightly tapered design. So you should know the difference between shaft, axle, and spindle. Shaft where we are using. Shaft is always rotating component. I mean axle is mostly non-rotating component. Spindle is rotating component but a small length of the shaft but a tapered design. I mean where we are using in machine tools, especially in lathe machine. Okay, these are the things very important and application you should know. You may expect some of the questions from this so this part. I mean for objective, I mean objective one or minor one. Okay, now we discuss a counter shot and jog shot and line shot. I mean counter shot and jog shot almost is similar. Okay, line shot is, the lines are considered, I mean number of shaft connected in axial direction with the help of the couplings, where I mean large distance apart transmission required. In that place we are using the line shot. Okay, I will show you some video. Okay, before then we go for the today discussion. Now where we are using the short applications. So up to that yesterday in the last class we discussed. Now we go to today's lecture here. Now see here. First I show you the sum up of the video. Then we come to this discussion. Then you can easily understand.
Manual transmission.
Are you able to see the video? Yeah, Kalyan?
Yes, sir. Yes, sir.
Or simply a gearbox, has been serving automobiles well for many decades. Even today, it's the most popular form of transmission. In this video, we'll give a concept.
This is example for counter shot. See, I mean here I think I hope that you're able to see my cursor. This is a one shaft. In the shaft, the top shaft connected to multiple gears, the bottom shaft connected to multiple gears. The two shafts, this is we are using for the power transmission. This kind of system design is counter shaft.
Conceptual introduction on the workings of an actual manual transmission with a reverse gear.
Especially, I'm showing this video for understanding the counter shaft.
Is why transmission transmission is required in an automobile. The power generated by the engine flows through the transmission before it reaches the drive wheels.
See here, I mean, the shaft power transmission from engine to gearbox, engine to flywheel, flywheel to clutch, clutch to gearbox, gearbox to, I mean, propeller shaft, then propeller shaft to universal joint, then, I mean, power transmission through propeller, I mean, transmitted from gearbox to differential unit through propeller shaft. The propeller shaft connected with the universal joint, because I tell you the reason, when we are driving the vehicle, when we are riding the vehicle, right, in the road is not a plain surface, some undulations, some rough surface. Then during that time, the rod, suppose if we are not using universal joint in this place, then what will happen? Then it will be the rod, the propeller shaft going to be bent. Then the power transmission cannot happen. Hence, we would like to avoid that bending effect. We are using the universal joint in the middle of the propeller shaft. Okay. Then power transmission can be done easily. Even the load, the road conditions or undulations or rough surface, smoothly power transmission can be done from gearbox to differential unit with help of this mechanism, propeller shaft, and I mean with help of this propeller shaft and universal joint. Okay.
The basic function of the transmission is to control the speed and torque available to the drive wheels for different driving conditions. For example,
see here, I mean, this is our differential unit, right? This is our, I take my pen. This is our differential unit. In this differential unit, I mean, the axle is hollow shaft, right? The axle is hollow shaft. The hollow tube, sorry.
Hill, you need more torque.
The axle is hollow tube here, right? In the shaft is connected in the differential unit. The shaft, left side shaft connected inside the hollow tube of the axle. Then that inside the hollow tube, the shaft is connected from differential unit to our wheel drum. Okay. So similarly in the right hand side and left hand side. So the axle is outer tube, that is stationary. It's holding the wheel securely and also allow them to rotate in the both wheel. That's all. So, but the axle is going to be subjected into bending moment. I mean, for example, if you consider the load here at the both corners of the axle subjected to load. I mean, both wheels are connected, and the center also differential unit. Differential unit is very less load only. But as compared to our body weight, our vehicle full weight will be shared in the two wheels. Hence, we can consider this simply supported beam.
For example, if you want to climb a hill.
Okay. Now you see the video. Carefully see the video.
You need more torque. By reducing the speed at the transmission, we will be able to achieve higher torque for the same power input. Conversely, if the torque demand is low, we can increase the transmission speed. Now, let's look at its inner workings. Manual transmissions work on the simple principle of gear ratio.
Anyway, this is the overall view for our subject. This video will give you about shaft, gears.
Here, the input and output shafts are connected through a counter shaft. A three-speed mechanism will look like this. It is clear that just by sliding the gears, we can achieve different transmission ratios. This transmission is more specifically called a sliding mesh transmission. They are good for controlling the speed, but they have an inherent disadvantage. It's quite tricky to slide from one gear and engage with another gear. constant mesh transmission permanently solves this problem. Here, the gears are always in mesh, but with a major difference. Here, the output gears are loosely connected to the shaft. If we connect only one gear to the shaft at a time, the shaft will have the speed of the connected gear. With the help of a hypothetical connector, different gear ratios are illustrated here. That in fourth gear, the input and output shafts are direct. It is interesting to note that in fourth gear, the input and output shafts are directly connected. The art of locking a loosely held gear to the shaft effectively and smoothly lies at the heart of the manual transmission. Let's see how this is done in actual practice. First of all, the main shaft gears have a synchronizer cone teeth arrangement. A hub is fixed to the shaft. A sleeve that is free to slide over the hub is also used in this system.
So this is the outer surface. I mean, whatever I told you, the briefly explained about the content, each content, hub and sleeve coupling, right? So that's what, I mean, you can understand these components. What is the counter shaft? How the gears are connected, how the power is transmitted from input to output shaft through counter shaft with the help of the gear mechanism. So that's what I would like to show you this video. This video not only for, I mean, short, it was some more information we are getting.
It is clear that if the sleeve gets connected with the teeth of the synchronizer cone, the gear and shaft will turn together, or the desired locking action will be achieved. But during the gearbox operation, the shaft and gear will be rotating at different speeds, so such a locking action is not an easy task. A synchronizer ring helps to match the speed of the gear with that of the shaft. The synchronizer ring is capable of rotating along with the hub, but is free to slide axially. Before moving the sleeve, the clutch pedal is pressed. This way, power flow to the gear is discontinued. When we move the sleeve will press the synchronizer ring against the cone. Due to the high frictional force between the synchronizer ring and cone, the speed of the gear will become the same as the shaft. At this time, the sleeve can be slitted further and it will get locked with the gear. Thus, the gear gets locked with the shaft in an efficient and smooth way. The same mechanism is employed to shift to other gears, such as first gear. And fourth gear.
Okay. Yeah, anyway, this is interesting one. Yeah.
Third gear. And fourth gear. You can also see the gear lever changing mechanism. A fifth gear is used to turn the output shaft at a higher speed than the input shaft. Now let's see how the reverse gear works. The reverse gear uses a 3-gear arrangement, as shown. Out of those, one is the idle gear.
Okay, anyway,
When the idle gear is
I'm going to put this
connected
video
to
in the
other
LMS,
two
you can
gears,
see
the
that.
output shaft will turn in the reverse direction. Please note here that the reverse gear does not have a synchronizer ring mechanism. This means that the gearbox rotation has to stop completely before applying the reverse gear. Thank you for watching the video.
Sure, I will share you the link. You can watch it later. Okay. Now I come to this. This is example for how the power is transmitted with help of the counter shaft using gear mechanism. Okay. Now I come to the next video. Rotary and drive shaft.
In episode 1, we touched upon rotary shafts and drive shafts. Now we will dive deeper into the differences between the two and application examples. If you need a refresher on any of the past shaft videos, they are all posted on our page for your linear shafts, except they are designed to transmit torque and withstand torsional forces. The most popular use of these shafts is in power transmission, more specifically with timing pulleys and belts. The shafts are mounted onto the pulley in a variety of ways, such as a keyway or set screw. For the keyway design, the rotary shaft must be designed with a
Here the how the pulley is connected on the shaft with the help of the keyways. We need a set screw. I mean, you see this is a top one set screw, bottom. I mean, here you can see that keys. Either we may use key or set screw to securely connect our pulley on the shaft, because it should not be a self-rotate. Then it cannot be a power transmitted. Hence, we are using keys or set screw. Hey, are you able to see my cursor, Kalyan, while explaining that?
Yes, sir, visible.
Yes, sir.
Okay.
keyway slot to match that of the pulleys. For the set screw design, the rotary shaft will have a set screw flap so that the screw from the pulley can tighten onto it. These styles apply to both rotary and drive shafts. But what's the difference between rotary and drive shafts? Let's take a look. The biggest difference between the two are the tolerances. Rotary shafts have lower tolerance standards, whereas drive shafts are high precision machined with higher tolerance standards. Here is a chart showing the circularity tolerances of rotary and drive shafts. The drive shaft tolerances are shown in parentheses. As you can see, the drive shaft numbers are smaller than the rotary. This circularity tolerance is important as it relates to the shafts rotating accurately without causing unnecessary vibration. Since drive shafts have a higher tolerance, these shafts are recommended for use in applications with high speed, and rotary shafts for moderate speed applications. Drive shafts have a tighter length tolerance than rotary shafts. This is because drive shafts can be used for direct mounting, where the length tolerance is important. Here are the tolerances of rotary shaft lengths, showing that tolerances are different depending on the length range. Compared to drive shafts, they have a tolerance of plus or minus 0.2 millimeters at any length. There are many ways rotary shafts can be applied to applications. Here are a few examples highlighted from the Masumi InCAD library. In this application, the rotary shafts are used to transmit the torque generated from the motor to the pulleys they are mounted to. The shafts then move the machine's arm to move the rods. Here is an application where a rotary bearing is used on the rotary shaft. The shaft is supported on one side via support and bearing. It transfers the motor's power to the winding drum, which then lifts the workpiece block. This rotary shaft application utilizes the snap ring alteration at each end of the shaft. The shaft is used in a roller to press a rubber workpiece into the concave portion of the other workpiece. The load to press the rubber is adjusted via the spring and bolt. Masumi rotary and drive shafts can be configured with a variety of alterations, including threaded, tap, D-cut, X-hole, wrench flat, stepped, and hollow. These alterations can be configured to lengths of up to 0.1 millimeter increments and in combinations to fit your application needs. This concludes the series on shafts. Thank you for tuning in, and be sure to check out our other videos.
The last one. Yeah, please see that.
Previously on MechMinute's shafting series, we covered the primary considerations when selecting tolerances and fits. All past videos are posted for your reference so that you can get caught up on this week's episode of linear shaft applications and related alterations. Linear shafts, in conjunction with linear bushings, are primarily used to transport a load. Because of this, most of Masumi's linear shafts are hardened and or coated to withstand the natural wear from the application. It is important to note, if your application is not transporting, but simply supporting a load, you will find cost savings in configuring a Masumi structural post instead. Masumi offers over 36 different shapes when configuring a linear shaft. This, accompanied with 26 standard alterations, allows for maximum customization in your mechanical design. Masumi alterations are additional machining processes that ease the assembly process. For example, high precision length and diameter tolerances can be selected for tight clearances. Or wrench flats can be added to prevent rotation while torquing fasteners. Generally, alterations are available for all configurable components. Along with a vast selection of linear shafts, Masumi offers complementary accessories to provide a full solution. In this example, a workpiece is lifted in order to transition to the next station. 4 linear bushings with rolling elements ride along the linear shaft to provide a smooth, low-friction guide throughout the entire stroke. These bushings are offered in many shapes and sizes to accommodate your requirements. Here we can see the pillow block bushing is chosen due to the mounting orientation. As the bushings actuate toward each other, the workpiece guide centers the unit on the conveyor. Shaft supports are also used in the application to position the linear shaft in a precise location. As you guessed, these are also available in various styles and can be configured with extreme precision. This next application depicts a positioning mechanism. The hand wheel drives a lead screw, which converts rotary to linear motion. The linear shafts are used to help support the load and prevent rotation caused by the lead screw. Shaft collars are another commonly used component that complement linear shafts. This application shows their 2 main functions, supporting a shaft and providing a mechanical stop. In this position, the collar can be directly mounted to a surface and act as a shaft support, or they can be affixed to the shaft to limit the stroke of the linear bushings. Masumi also offers collars with urethane padding to dampen the impact of metal-on-metal contact. With millions of components available, Masumi offers a one-stop shop for your mechanical design. Now that we're
Okay. I think you might have been understood linear shaft and drive shaft and rotary shaft and counter shaft. Now the last one is I would like to show you that line shaft. See here, the line shaft. This is a main power transmission line, right? This is a main power transmission line. But see here, there are, from this main power transmission line, in between we are using pulleys 1, pulley 2, or pulley 2 here, 3, 4. For different applications, we are taking the power from the main shaft. This is example for line shaft. You might have been seen if you go to that any rice mill, you can see that the long shaft connected with the motor or engine, right? That long shaft will be connected to multiple machines for operating the multiple machines at the same time with the help of the line shaft. So this is one of the good example for the line shaft. Okay. Now this is a counter shaft. We already discussed in detailed manner. Okay. And these things also I put in this LMS, this PPT. These are the counter shaft. This is a jack shaft. Okay. Now the jack shaft in diesel in steam engine. See here, the jack shaft. Here, this is the jack shaft connected here. I mean, how the power is transmitted. Okay. Now this is a spindle where we are using. I mean, lathe machine also we are using spindle, and drilling machine also we are using spindle. Okay, I sorry, first I record it because oh. Earlier I showed video. Okay, so now this is a propeller shaft we discussed. Now I mean this is axle. I mean axle is mostly non-rotating shaft, and propellers are always rotating shaft. Power transmitted from the gearbox to differential unit through universal joint. Okay, I mean that axle is going to have bending moment, bending effect due to the both load. I mean both the wheels are connected at the end of this axle. I mean the load is full, the vehicle load, full load will be acting on the wheels, hence this is subjected to bending effect. I mean always this is looks like simply supported beam, simply supported beam. Okay, now the line shaft. This is the main shaft. I mean, this is the main shaft. The main shaft connected to multiple mechanism to access the multiple mechanism at a time. This is the main power transmission line. This is the main power transmission line. See here, in the main power transmission line, we are connecting multiple mechanism to drive at a time. I mean, see here, this is the pulley 1 connected in the main shaft for accessing this mechanism. Accessing this machine. This may be pulley 2 connected to this mechanism for accessing the machine 2. I mean, similarly, we can connect it, pulley 3 with machine 3 or machine 4 or 5 like that. I mean, the similar mechanism, the line sort mechanism we are mostly using in the rice mill. If you go to any rice mill, you can see that the long shaft, the line shaft connected in the main power motor or engine. From that line shaft will later the line shaft will be connected to multiple mechanism to drive the multiple mechanism at a time. So that is the line shaft application. Okay. Now counter shaft, I have shown you video earlier. It's a clear explanation. This is a counter shaft. I mean, the power transmit. This is the input shaft. This is the output shaft. I mean, in between, this is a counter shaft. The counter shaft connected multiple gears. So based on our requirement, the speed going to be reduced with the help of the counter shaft mechanism while connected to the appropriate gears. Now, this is also counter shaft. Example, this is a jack shaft. I mean, also called intermediate shaft. Jack shaft application in steam engine. Okay. Now, this is a spindle. I mean, spindle. Now we discussed spindle in the lathe machine. Here, the spindle in drilling machine. This is a spindle in drilling machine. Okay, the small shaft is slightly tapered design, and the length of the shaft is very small. Okay, I mean most of the machine tools, a lathe machine, milling machine, drilling machine, we are using a spindle. Okay, small length of the shaft. Now this is the hollow shaft we'll discuss later. Now I come to our regular discussion. Okay, design, shaft design. One more thing I'd like to show you, line shaft keys. I mean, in the video I've shown you the keys and coupling. Just keep in mind, later we are going to discuss that time, very useful. This is the keys, see here. The keys, how it will be connected. See, this is our gears, this is our shaft, the gear. This is our gears. Sorry, this is the gears, this is shaft and keys. With the help of the keys, how the gear is connected. Okay. Now, anyway, we are going to have a separate content types, different types of keys, and how the load is acting, keys and key design. There are different types of keys we are going to discuss. Just square key, flat key, and round key, Kennedy keys, tapered pin, hip guided key. These are the things we are going to discuss. Just now keep in mind. Okay. Now I come to this our shaft design now. Okay. Now see here, shaft application. Now see this, there are shaft is not a limited application. Okay, it's not a limited application. See here, shaft. The shaft are using in the power generation place. Power generation place. I mean the shaft inside the generators and motors are connected. So with the help of this shaft, the generators, I mean power generators and motors or power generators or turbines going to be connected with the help of the shaft. Okay. Now, I mean you might have been seeing camshaft in IC engines. Camshaft, what is the application of camshaft? Anyone please reflect? What is the application of camshaft? What is application?
Operation of valves.
Yeah, thank you. I mean, valve activating mechanism. Camshaft, with the help of the camshaft, we are activating the valve mechanism, right? Now, crankshaft, where we are using crankshaft, what is the application of crankshaft? Anyone, please? Crankshaft.
Movement of piston
Which one?
in engines.
Okay, I'm not getting clearly because your voice is breaking. Anyway, thank you for reflection. I mean, crankshaft. Here, that reciprocity motion is converted into rotary motion with the help of the crankshaft. Right now, this is the steel shaft. The steel shaft. I mean, you might have been seeing windmill that where long blade. It's connected with the this kind of very bigger shaft because that is very heavy load is acting on the shaft. Hence, the shaft dimensions will be very high. Diameter is high. Now, whatever we discussed earlier, now this is the car rear axle, right? This is the train wheels and axles, right? Now this is the crankshaft inside the crankcase. I mean propeller shaft of this heavy duty helicopters. Now you see here propeller shaft. Okay. Now these are the things. I mean for example, shaft application. Now we come to the shaft design now, design of shaft. The design of the shaft can be done in different methods based on strength basis, based on torsional rigidity or lateral rigidity, and based on ASME code based on ASME code concept. Okay, now first one by one we see that shaft design based on the strength basis. Now the design of the shaft can be determined by, determined design of the shaft or shaft diameter can be determined through strength basis and rigidity basis. First we see that. I mean, these are the things we already discussed in the DME or strength of material in the earlier subject, which one you studied in second year and third year. Now, first thing I'm taking, when the shaft is subjected to axial tensile force. When the shaft subjected to axial tensile force, we are going to use direct formula. Force by area. I mean, then P by pi by 4 d square. From this, if the permissible tensile stress is given, then directly we can calculate this diameter of the shaft. I mean, at which condition we can consider this direct tensile load? Anyone please reflect? At which condition? I'm telling that sigma t is equal to 4p by pi d square. At which condition we can consider this formula for design the shaft, for design the shaft or for define the diameter of the shaft? At which condition?
When axial tensile force is acting.
Axial?
Tensile force.
Yeah, that is correct. Exactly correct. But at which condition? Dynamic load condition or static load condition?
Static, sir.
Yeah, static, very important. I mean, even when you take this is the shaft is connected the load, right? Now this is the shaft is rotating. The shaft is subjected to I mean the shaft is subjected to tensile load as well as twisting moment. When this load is rotating, when the mechanism is rotate, mean now the shaft is vertical condition. Now the shaft subjected to tensile load, direct tensile, as well as the shaft is transmitting the power. Then in this case we have to consider torsion as well as tensile load. But especially this formula only for static load condition. I mean the first formula only we can use for static load condition. Now the second one, bending load, right? Now when the shaft is subjected to bending moment, see this is the when the shaft is subjected to bending moment. Now this is you are very well known, right? This is sigma b is equal to 32 mb by pi d cube. Now, right? How it came this? I mean, this is came from like our bending moment governing bending equation, right? M by E is equal to sigma b by y is equal to d sigma b by y is sigma b by y, right? From this formula, we derived this sigma b is equal to 32 mb by. Anyway, just recap. I put that also. No problem. Just 1 minute. I spent time. I mean, what is the bending moment? Bending moment governing bending equation. M by y is equal to d by 2. I is equal to pi by 6 pi by 64 into d power 4, right? From these relations we can find out what is sigma b. Sigma b bending load, bending stress, right? Bending stress at 32 mb by pi d cube. Similarly, torsional moment. With respect to torsional moment, the design of the shaft can be defined torsional moment, right? What is torsional moment? T by J is equal to G theta L by G theta by L is equal to tau by R, right? Take these two torsional moment, take to this two relation. I mean, now only we are discussing about bending stress, right? And shear stress. We are not thinking about this torsional rigidity. That will come later. Now only I am taking these two component. Then define this tau is equal to now. I mean 16 mt. This t, the t is nothing but I am considering torsional moment mt divided by pi d cube, right? Now this is the, I mean, if you know the permissible shear stress, then you are able to find out the diameter of this shaft with respect to torsional moment acting on the shaft. Now if you know this permissible bending stress, then you are able to define the diameter of the shaft from this It's the relation, bending stress relation. Okay. Now this is the relation. Now tau is equal to, now, I mean, you may expect this type of objective questions. What is sigma b in this case? In this case, sigma b, what is the sigma b in this case? Sigma b is equal to 2 times of tau. When we are considering both torsional moment and twisting moment acting on the material, identical material, hence the sigma b bending stress is twice the torsional, I mean shear stress. Shear stress. Now I come to the maximum. Now, I mean, this is the things with respect to torsional moment and twisting moment. We can define the our diameter of the shaft. Now when the shaft is subjected to a combination of the loads, then it's going to be play with principal stress, right? That's we know, right? What is the principal stress? Maximum principal stress? Then maximum principal stress sigma 1 is equal to sigma x by 2 plus square root of sigma x by 2. I mean, when we are combined torsional, I mean shear stress and bending stress, I mean bending stress is nothing but normal stress. Normal stress and shear stress are playing, then Mohr circle is important role. Mohr circle is going to play in the important role. Hence that's what we are saying here, Mohr circle. I mean, this is the y-axis shear stress axis, x-axis is a normal stress axis. I mean, nothing but the bending stress. Now, see, this is the, I mean, what is this? This is sigma 1. You might have been studied in the early, I mean, the early subject is DME and on the strength of material, sigma 1. Sigma 1, yeah, this is nothing but sigma x by 2, right? This is nothing but, this is sigma x. Sorry. This is sigma x, this point. This point is sigma 1. Now this is sigma x by 2 from this point to this point, sigma x by 2, right? Now, I mean, what is this point? This is nothing but shear stress. This is nothing but shear stress. Now, how can it, I mean, this is, I mean, maximum principal stress, maximum principal, this is a tau max. Now, just a small derivation, I do it here. Then we try to close the meeting today, and tomorrow we slowly we increase our speed of the discussion. Now, okay. Now, what is sigma x in this case? Now, I mean sigma 1. Sigma 1 is here. How can it define? Sigma 1 is equal to, I mean, OE plus, here I am taking this one. OE plus EF. Sigma 1 is nothing but OE plus EF. OE plus EF. What is OE? OE we know very well. Sigma x by 2. Then sigma 1 is equal to sigma x by 2 plus square root of, right? I mean sigma x by 2 square plus, I mean tau square, right? That is here, this triangle. Now this is what is this? This is now, I mean, EF is equal to EB. EF is equal to EB. I write it clearly because you may not see here. Here, EF is equal to EB, right? Now we know that this is EF. This EF is equal to EB. Then EB. What is EB? This is hypotenuse side. Now apply this. It's a very simple concept, right? Now this is, I mean, this is nothing but, I mean, we know already sigma x by 2 whole square plus we know already this. This is our tau. This is our tau, right? Sigma x by 2 whole square plus tau square. Then whole square root. That will give you EB. Hence, I put this. This is my EB. EB or EF, right? Now this is our maximum principal stress. Now maximum principal stress. Now, I mean, what is that tau max? This is tau max. You already very well know. Tau max is equal to this part, EB part. Now this part we are going to use for design the compound, design this our shaft component. Now, I mean sigma x, as I told you earlier, sigma x I am considering here bending stress, normal stress, bending stress, bending stress under normal stress, hence 32 MB. This is our sigma x, 32 MB by pi dq. I mean this is our tau. Substitute in this equation maximum principal stress equation and maximum shear stress equation. Then finally you are going to get this. Sigma 1 is equal to 16 divided by pi d cube into, mb plus, because now I would like to write my equation in terms of bending moment, because here early we the sigma x, sigma 1 is a stress. Now bending stress. Now how much bending moment is acting in the beam? Bending moment is acting in the shaft. How much bending moment is acting in the shaft? How much twisting moment is acting in the shaft? Right? Based on that, I would like to design my shaft diameter. Hence, in this maximum principal stress theory, I would like to introduce my bending moment. I would like to introduce that stress value in terms of bending moment. Hence, this equation sigma x is equal to, sorry, now sigma x we are writing in terms of bending moment. We are writing in terms of bending moment. So 32 MB by pi d cube. Then substitute here. This is now our sigma 1 based on maximum principal stress theory. Now come to maximum shear stress theory. We know, right? This is our tau max. Substitute in MB. Here tau max, then it can be written in terms of bending moment and twisting moment. From this, we are able to define our diameter of the shaft. Now see here, the left hand side, whatever we discussed, the left hand side, see here, this is sigma 1. The sigma 1, how can I define? We already discussed in the DME, design of meson element. Sigma 1 is equal to nothing but the permissible value SYT divided by FOS. Yield strength divided by factor of safety. We already discussed in the earlier subjects. Hence, here I am introducing sigma 1 is equal to SYT divided by FOS for safe design. For safe design, I am introducing this concept. I am introducing the factor of safety for our safe design of the shaft diameter. Now, similarly, I am introducing here tau max. Tau max is equal to, we already discussed in the DME subject, right? 0.5 times SYT divided by yield strength divided by FOS. This will give you permissible stress limit. That permissible stress limit, also called safe limit, for design our shaft component, for design our shaft diameter. Now, finally, see here, as per the experimental investigation, people suggested that, as per the experimental investigation, people suggested that that maximum principal stress theory is good for the brittle material. But which shaft made of ductile material? Then this theory is not applicable. You may expect this type of question in even any competitive exam. Maximum principal stress theory, it can be suitable for, it can be used for the brittle material, not for ductile material. Very important, because people gone to many experiments, trials. Finally, they came to know that this theory is applicable for brittle material. When we are using shaft in brittle material, then we have to go for shaft design using this equation. Okay. Now, ductile material, we can use the shear stress theory. Ductile material we can use shear stress theory. Now I come to that later. Ductile material we can use shear stress theory. Okay. Now, yeah, any doubt, please? Please go ahead if you have any doubt. Now, equivalent torsional moment, equivalent bending moment. Now, what is equivalent torsional moment, equivalent bending moment? Now, square root
Sir,
of, yeah, tell me, Pa.
sir, already it is 9:40.
Okay, I stop it here. Tomorrow we complete, tomorrow we are going to discuss this and we discuss the problem. We start the problem tomorrow. Okay. Very simple concept. Equivalent torsion moment, equivalent bending moment. We will discuss tomorrow class. Also, we will discuss the torsional rigidity and a soft design based on ASME code concept. We are going to discuss in the next class. We have to complete next class some of the problems based on this concept. Okay, guys, I stop it here. Please go ahead if you have any doubt. Kalyan, I'm going to take attendance. Still 67 students are there. I'm waiting for that. Next, this is the first 1 or 2 classes. I'm giving you freedom. Next class, sure, I'm going to take the attendance. Please inform the students. It should be 89 students or 88 students are there. Only 66 are here. 66 or 65. Remaining 23 students not here. Please inform them to attend the class.
Yes, sir. Right.
Yeah, please, if you have any doubt, please go ahead. Okay, Kalyan, I am closing the meeting. Okay.
Yes, sir.
Thank you, sir.
Thank you,
Thank
guys.
you, sir.
Yeah, thank
Thank you,
you.
sir.
Yeah, thank you, Pa. Thank you.